Jap. Hmm.
Dah.
Dah.
Okay, Assalamualaikum warahmatullahi wabarakatuh and very good evening to all of you. So today our group is going to present about our analysis about bullet. So first of all, my name is Azmirul Kimil Azmi and my two other friend which is Muhammad Hadri bin Aziz and Amirul Iman bin Kamsi. So for the introduction, which is our group is analyst about bullet. So this is the picture of all the bullet. Actually, the bullet is only number one, but to ensure that the bullet is working, we need all of them. So number one, which is bullet. Number two is case, which is to keep it together. Number three is propellant, which is the main material to ignite the bullet. Number four, which is the rim, to allow the extractor to make the bullet stable. And number five is the primer, which is to ignite the bullet. So this one will continue with my friend.
Okay, so for the problem statement, a great bullet is a bullet that has excellent performance. The performance of a bullet is determined by the accuracy and the distance traveled by the bullet. There are some factors that can affect the performance of a bullet. Some bullets can easily drop off from the target and some bullets drop early before they reach the target. Therefore, in this study, we will investigate the effect of downforce and drag lift towards the performance of the bullet. The downforce and drag lift of a bullet will be discussed precisely from the tests and simulation that were obtained at the end of this study.
Okay, so for the modeling stage, I'm going to in charge. So our main objective is actually we want to compare which bullet are giving the best performance. So like from the which bullet can go further and can give more acceleration. So we using Katia V5 R19 in modeling stage. So the first step is the bullet were designed in part design section and XY planes were chosen before selecting the sketch. And then for bullet 7.62 times 39mm bullets, the top view of the bullet was drawn in 2D, but only half of it using the two lines. And then after sketching it in 2D, we exiting the workbench, and then we click on the shaft command to make the bullet become 3D model. Then after that, we design the head of the bullet. We repeat the same step to design the head of the bullet. And then after that, we click on the shaft command to turn it into 3D part. Then after that, yeah, we using the same step for the 0.22 LR and 0.5 BMG bullet. Next. Okay, so here are the blueprint of the bullet. Okay.
Okay, so this is going to be my part. So I will explain briefly about this first, then I will show you at the ansys. So after we done model to the ansys, so first thing we must which is we firstly import selected file, then we edit it in the space claim, which is we need to repair a bit of the design. Maybe the design has two different faces, so we make the faces become one. After that, we go to the design modeler. We import we must import the model and we generate it. Then we change the size from meter to millimeter because our bullet is very small. Then we should make an enclosure which is the main part for the simulation. Then we select target bodies, which is the enclosure, and selected bodies, which is the bullet. Then we generate the enclosure. After that, we create Boolean. Boolean is basically we just name the faces of the enclosure, which is inlet, outlet, and wall. And then we generate the Boolean. That's all for the geometry. After we're done with our geometry, we are going to do meshing. So, so to make the meshing, we just click on the mesh, and then we set our element for 1 mm. So this 1 mm is various for all the model, but our bullet we just make it constant for 1 mm because as I say just now, our bullet is very small. So we set our element order to program control, and if we don't want to put it program control, we also can make it as quadratic. Then we change the sizing adaptive from no to yes. So for the CFD, which is we select fluent, firstly we change the viscous to the Ka epsilon. Then we make sure that our working fluid for this simulation is air. Then we set our velocity in the boundary condition, which is our constant velocity is 850 meter per second. Then we change the name of the axis, which is drag and lift coefficient, which is the purpose our simulation. Then we change inertialization to hybrid inertialize. Then we set our 20 iteration to run the CFD. Basically, the iteration number, if we make it bigger number, then the drag and lift coefficient we get more precise. But our situation that we make low iteration because our performance laptop is quite low. So now I will show you our project at the ansys. So this is what I said just now. This is the geometry, mesh, and setup. So I will show you only two, which is meshing and setup, which is CFD. So this is mesh. First thing, because you see this box is called enclosure. So to make the mesh, we just click here, mesh. Wait. So these are the mesh. Yeah, here. We can see here, we change the element size to 1 mm, and the element order is program control, and the sizing is yes. After that, after done with meshing, we go to fluent. First thing, we just make sure that, wait, hold on, our viscous, which is K epsilon. Maybe it takes quite some time to generate it. Yeah, so these are K epsilon. Maybe I can't show you all of that because my laptop is lagging. So I just say now, okay. So yeah, it's still loading. So I'm sorry of you because I can't show you. Maybe we just proceed with our presentation.
Okay, so for the result, firstly, we need to know the list of formula that we use for the experiment. Okay, so this is the list of formula we have the first one, we have drag force, and then we have the lift force and drag coefficient, and last one we have lift coefficient. Okay, so we have fixed from the ansys, we have fixed that the speed of bullet is 850 millisecond. Okay, so from the table one shows the drag coefficient and lift coefficient for each type of bullet. Okay, so we can see that for the drag coefficient, we have the highest one is 0.5 bmg, and for the lift coefficient, the highest one is also 0.5 bmg bullet. Okay, so for the table 2 shows the drag force and the lift force exerted by the fluid towards bullet. Okay, so for each type of bullet, we can calculate the drag force, the total drag force, and the total lift force for the each bullet by using the coefficient that we obtained at table 1. Okay, so from this table, we know that the highest drag force for the highest bullet, that the highest drag force for the bullet is 19.584, which is the 7.62 type of bullet, and for the lift force, the highest bullet that have the highest lift force is 0.5 bmg, which is 0.573. Okay, so from the so from the experiment, we should know that a great bullet has a high lift force but a low drag force.
Okay, so in conclusion, to sum up, based on the ansys analysis and the calculation that were made, 0.5 bmg bullets have given the best performance compared to 7.62 times 339 millimeter and 0.22 LR bullet. It is because 0.5 bmg has the highest lift force and also get a second place on the drag force. Okay, I think that's all from us. Thank you.
Thank you.